We're going to work an exponential model given an initial point and a rate. The example we're going to work states a population is currently at 11,000 and grows at 8.2% each year. Suppose P represents population and T represents the number of years of growth. An exponential model for the population can be written in the form P of T equals A times B to the T. The tasks we will perform are finding the model, predicting the population in 5 years, and finding the time it takes for the population to reach 20,000. Now, these tasks are build a model, evaluate, and solve. Pretty much the three basic tasks we would do in a problem like this are all captured here. Now, to find the model, there's something interesting to note about the relationship between what's been given and the parameters A and B. So to build the model, we need to find A and B, the parameters. Now A will correspond to the initial point, and that is, so basically what we observe is the population is 0, the time is 0 and the population is 11,000 right at the beginning there. And if we plug that in to the prototype, P equals A times B to the T, we get 11,000 as the output is equal to A times B to the 0. And B to the 0 is 1, and A times 1 is going to be A. And so this equals A, telling us that A is equal to 11,000. And so our model is P equals 11,000 times B to the T. So that was to find A. To find B, using the rate, we need the relationship as follows. So B will be related to the rate. Now, if it's growth, B will equal 1 plus R. And if it's decay, B will equal 1 minus R. For decay, you'll see things like it drops 10% each year, or it drops 5%. So you would just subtract the 5% from 100% and you'd get 95%, for example. So that's how you get your B, whether it's growth or decay. Our problem that we've been given is growth, so we're going to use that one. And we have the growth rate 8.2%, which as a decimal is 0.082. And so B is going to be 1.082. And this gives us the model P of T is equal to 11,000 times 1.082 to the T. And now we're going to use this model to evaluate and solve. In the second task, it basically is asking what is the population in 5 years. That's essentially the question. So we see here time is known, time is the input. What is the population? So population is unknown. Population is the output. And when you see that combination, input known, output unknown, this is evaluation. So we're just going to plug in t equals 5. And this comes out to approximately 16,313. Whatever it is, people, critters. We'll say individuals. Now you can't have a decimal number of critters, and so that's why we've rounded to the nearest whole number. Lastly, when is the population 20,000? So we look at this, population is known, population is the output, when means time is unknown, time is the input, and when your input is unknown and your output is known, this is solving. So what are we going to solve? We're going to solve 20,000 is equal to our model, 11,000 times 1.082 to the t. And this is the same as solving an exponential equation. So solving an exponential equation means we need to isolate the exponential and then use logarithms. So we will begin by dividing by the 11,000. This will isolate the exponential. So we have 20,000 divided by 11,000 is equal to 1.082 to the t. Now we will log both sides. And what we have is log of 20,000 over 11,000 is equal to log of 1.082 to the t. And the power rule for logs pops that t out front. So we have log of 20,000 divided by 11,000 is equal to t times log of 1.082. And the log of 1.082 is just some number, so we can now divide. And we have t is equal to log of 20,000 divided by 11,000. And all of that is divided by log of 1.082. Now, this is a story problem. And if this were real life and somebody asked you how long it took and you told them it took log of 20 divided by 11,000, all of that divided by 1.082, if you told them that, they would probably not understand what you're saying. So it would be better if we gave this as a decimal approximation. And doing that, we arrive at about 7.6 years.